Hello, my name is Başak Gözütok. I'm a freshman electrical electronics engineering student in Bilkent University, and today I will present my Physics 101 lab project named Effect of Moment of Inertia on Rolling Motion on an Inclined Plane. The experiment investigates how the moment of inertia affects the rolling motion of different objects, a disk, a ring, a sphere on an inclined plane. The main goal was to compare theoretical and experimental results for acceleration, analyze how energy is divided between translational and rotational motion, and understand how moment of inertia influences descent time. When an object rolls down an incline without slipping, its potential energy is converted into both translational and rotational kinetic energy. The inertia coefficient defined as k is equal to the moment of inertia divided by the product of mass and radius squared, is a dimensionless number that shows how the mass of an object is distributed relative to its axis of rotation and determines how much of its energy goes into rotation versus translation. A ring has its mass far from the center, giving it the largest inertia coefficient k. A sphere has the smallest k, while the disk lies in between. According to theory, objects with larger k should accelerate more slowly. In my experiment, I measured the mass and radius of each object and set up my inclined plane. I released the objects from the same height and recorded the time with a stopwatch. When measuring with the stopwatch, errors of 0.1 or 0.2 seconds can occur due to human reaction time. To prevent this, I repeated the procedure 5 times and dropped every object 5 times from the inclined plane and took the average of the measured times. I also slowed down the videos I shot during the experiment to verify the measured times. In my experiment, the ring had the longest descent time, while the disk was the fastest. The sphere was expected to be faster than the disk, but in practice it was slower, mainly because of its larger mass and tendency to slip. The discrepancies in acceleration mainly arose because the experiment wasn't perfectly ideal. Friction and stopwatch delay affected all objects. Moreover, the discrepancy between the measured times of the sphere and the disk can be attributed to slight differences in their masses. If both had exactly the same mass, the measured acceleration order would have matched the theoretical prediction. As for my results, the sphere showed the largest error in acceleration between theory and experiment, about 25%. The ring and disk had smaller errors, around 8%. As seen in graph 1, all points fall below the ideal line, showing systematic energy losses due to friction and air resistance. However, the energy distribution ratios match the theoretical predictions almost perfectly, as shown in graph 2. This means that while friction and slipping reduce the overall speed, the fundamental principle of energy partition based on moment of inertia was clearly observed. In conclusion, the experiment was successfully demonstrated the relationship between moment of inertia and rolling motion. To improve accuracy in future studies, photographs could be used. Symmetry surfaces could reduce friction, and objects with equal masses would isolate the effect of inertia more clearly. Thank you for listening.